Hello, my name is Sebastián Vergara. I'm an associate professor for the Computing Institute within the School of Engineering at Universidad de la República in Uruguay. This work is part of my master thesis aimed at proposing an approach for controlling implementation compliance of formally specified microservices architectural patterns using event-B and model-based testing. In particular, this work is the first step towards that goal and is aimed at proposing a mechanism to formalize microservices architectural patterns with event-B. This presentation is organized as follows. First, I'm going to give a little bit of motivation. Then I'm going to talk about the formalization process of microservices architectural patterns, exemplified using the circuit breaker pattern. And finally, I'm going to give some conclusions on the future work. So, microservices have recently emerged as an architectural style, mainly driven by industry, in which applications are composed of small services running in their own process and communicating with each other using lightweight mechanisms. As with many other architectural styles in the past, architectural patterns have been proposed to guide the construction of microservice-based applications. These patterns document the existing knowledge and good practices for addressing recurrent situations. However, most of the authors describe them in natural language, hence not following a formal specification, which ultimately could lead to ambiguity as two different people could understand different behaviors just for reading the exact same thing. And I'm going to give you a couple of slides after an example of this. On the other hand, event-B is a modeling method for formalizing and developing systems that operate as discrete transition systems. Event-B is built around the notion of events, and its main purpose is to aid the development of systems that will be correct by construction. Therefore, in order to deal with ambiguity of informal descriptions, arises the idea of formalizing microservices architectural patterns with event-B. Also, how to formally prove the model in event-B, and finally, how to give those models an animation in order to visualize the specification behavior. In order to demonstrate the formalization process, I'm going to use one of the most popular patterns in microservices, the circuit breaker pattern. This pattern proposes the use of a proxy with the ability of immediately rejecting invocations to the microservice for a certain period of time after a consecutive number of failures. The result of invoking the microservice exceeds a specified threshold. After the timeout period, and in case the microservice starts responding failureless, the proxy resumes forwarding requests to the microservice. Otherwise, a new rejection period starts. As this one, and depending on the author, there are many other similar definitions for the circuit breaker pattern. For instance, consider the one Michael Nygaard, author of the book Release It, does. So what I'm trying to show here is that natural language generates certain ambiguity when it comes to understanding the behavior of a pattern. So considering the first definition, there are three participants in this pattern. A client who starts the flow by making a request, the microservice, that is what the client needs to invoke, and the circuit breaker proxy, an intermediary that decides when to forward requests to the microservice or when to trip and fail fast. The circuit breaker pattern behavior can be modeled as a state machine. As long as the microservice responds failureless, the state machine remains on the closed state. When the amount of consecutive errors goes above a certain threshold, the state machine transitions to the open state, where it will wait for a predefined amount of time before rechecking microservice status. While on the open state, the circuit breaker will fail all requests immediately. Once the timeout period elapses, the state machine transitions to the half-open state. From there, a set of test requests are allowed to come through. If all those test requests succeed, the state machine transitions to the closed state again. However, if any of them fail, it transitions to the open state again and a new timeout period is set. So once definition for the architectural pattern is established, the first step in the process of formalizing this architectural pattern is to gather all the requirements. These requirements can be derived from the pattern context or solution statements and describe the behavior the event B machine is meant to model. So here from font 1 to font 8 are all the requirements that could be extracted from the pattern context or pattern solution statements. The second step is to define the static parts of the event B model, also known as the context in terms of event B. So the possible states of the machine are derived from font 1. Font 1 implies the creation of a set constant containing all the closed, open, and half-open states. The same reasoning applies to the constant threshold, timeout period, and the amount of evaluation or test requests when in the half-open state. All of them defined as positive natural numbers in the event B context. Once having the context defined, the third step is to define what are called the machine variables and invariants. For example, from font 6 follows the need of having a variable to measure time. The approach defined by Sarasog and Butler to describe time as a discrete property was followed. Similarly, from font 1 follows the need of having the current state of the circuit breaker. That current state must belong to one of the elements described in the context, so in the previous step. After defining the context and machine variables and invariants, the fourth step is to define the transitions, which in event B terminology are called events. One event that must always exist is the initialization event. This event is meant to initialize variables defined in the previous step. For example, from font 2 follows the initial state of the circuit breaker, which is closed. Other events that imply transitions are receiving a request and the time-lapse event. This last event emerged from the approach proposed by Sarasog and Butler to describe time as well. Once the events are identified, it's necessary to define its behavior. In event B, events could receive parameters whose values are determined by a set of guards. In this slide, for instance, in line 3, it's represented a parameter, and the guards are those from line 5 to 11. Guards within an event could use any machine variable to define its behavior. Guard 2, for instance, is the only one that transforms a machine variable, and that's when the circuit breaker is in the open state and the timeout period has elapsed. Then, the new circuit breaker state should be half open. Finally, an event defines its actions, which are the ones that impact the machine variables, in this case moving time forward, and assigning the parameter value to the corresponding variable. This is setting the new circuit breaker state. Similarly to what was done for the clock event, must be done for the request event. Here, it can be observed all the event parameters defined for the request event. Then, all the guards for the closed and open states, combining the rest of the possible parameters. For instance, in line 18, when the current circuit breaker state is closed and the microservice is faulty, then define the value of the new consecutive errors variable to the amount of consecutive errors plus 1. This parameter value, new consecutive errors, is then used in the next guard, guard 8 on line 20. If the circuit breaker state is closed and the amount of consecutive errors is equal or greater than the threshold constant defined in the context, then the new circuit breaker state should be open and set the timestamp when the circuit breaker tripped to the current time. Similarly, here are depicted all the guards for when the circuit breaker state is half open, and finally, the actions of the event. Formalization enables formal proofs of safety properties of the model. For example, invariant preservation. These are carried out using the routing platform, which automatically generates proof obligations or POs and supports automatic as well as interactive proofs. POs specify what is to be proved for an event B model. Green ticked POs represent discharged POs. This means that all the safety properties of the model are valid. All those POs with an A in the picture are automatically discharged by the routing platform, whereas those with just a green tick were discharged in an interactive environment or manually. In addition, formalization enables model animation, which complements modeling and proving by providing the means to check that the model system operates indeed as expected, according to the specified requirements previously seen. In order to provide a visualization for the model, vMotion Web was leveraged. This tool, which is built on the ideas of vMotion Studio, enables the generation of an executable and interactive view bound to an event V model. So let me switch to the browser to show you the final results. So vMotion Web is based on the well-known languages and libraries such as HTML, SVG, JavaScript, and jQuery. With vMotion Web, events can be triggered directly from the visualization, such as we have just seen with the clock event. And also, when an event modifies any variable from the machine, it gets dynamically refreshed in the visualization. The same process as we have just seen with the circuit breaker pattern was also followed for another couple of patterns, the service registry and the service discovery patterns. In this picture we can see the vMotion Web animation done from the service registry and service discovery patterns modeled in event B. So In this work, I presented a formal approach for modeling microservices architectural patterns with Event B. This approach helps mitigating pattern misunderstanding or misapplications due to natural language ambiguity. It also helps to achieve a better comprehension of pattern runtime behavior as well as setting the grounds to building a correct by construction system. This work is the first step towards controlling implementation compliance of microservices architectural patterns implementation against a formal specification. As per what future work concerns, we are extending this formalization approach to other microservices architectural patterns and generating a modeling characterization. Another line of work is the one of generating abstract test cases that could be helpful to assess compliance of already implemented patterns against a formal specification. And finally, the ultimate goal is to combine multiple formalizations into a composite system and being able to generate code from the model so the end system correct is a correct by construction system. So thank you very much for listening.